Here we're going to talk about reactions between acids and bases, which are typically known as neutralization reactions. And from the overall reactions, we're going to figure out what the net ionic equations are for these reactions, and then this is going to lead us into reactions between acids and bases, doing some calculations for them. So typically an acid-base reaction produces water or a weak acid as a product. So this is going to be a little bit different than when we were doing precipitation reactions where an insoluble salt was the product. Here our product is still going to be dissolved, so it's kind of theoretical. But if you look, a lot of the times water is going to be a product of a neutralization reaction or a weak acid. And so you'll see that a little bit more here in just a second. So overall, the steps of finding the net ionic equation for a neutralization reaction are very similar to the steps that we use for a precipitation reaction. There's just a couple of extra concepts that we need to remember. And with that, the idea is when we disassociate a reaction to get to the net ionic equation for our neutralization reactions, you have to remember that we do not disassociate water and we do not disassociate weak acids. And so that's, once again, that's what leads us into knowing that these are our products, just like the insoluble salt was for the precipitation reaction. We didn't disassociate that. That's what led to our net ionic equation. So we need to have our products not disassociate. But this is the one thing that you need to remember is when we go to the complete ionic equation, you don't disassociate water or weak acids. So when we do look at this, strong acids and strong bases are disassociated. So just like our soluble salts, when we break them up to get to the overall ionic equation, we break them up into their ionic species. And then one of the things that does make it a little bit tricky is a lot of the times there's going to be soluble salts present inside of these reactions. So you're going to need to apply some of the rules of solubility. In this case, typically the only rules that you need to apply have to do with group 1 metals. So you need to remember things like sodium and potassium are soluble salts and that they are going to disassociate. But we will see some soluble salts. And during neutralization reactions, we do not expect to see any insoluble salts. So there should be no precipitates involved with this. So the first one, and kind of the classic one, is a reaction between a strong acid and a strong base, a neutralization. So this is the classic neutralization. And I give you a reaction. So we have our weak acid, HBr, reacting with our strong acid reacting with our strong base, so HBr reacting with KOH. Remember, we talked about before how to determine if something's a strong acid or a strong base, and this is where we get into the importance of being able to tell the difference between these two, because how we treat them later on is going to be different. So remember, it's important to be able to look at something and say, is it strong or is it weak? And we talked about that in the previous section. So we go ahead and we follow the same steps. We have this reaction, we draw the overall chemical equation, so we interchange the ionic species, and then we disassociate, and then we get rid of the species that are on both sides of our arrow. And so in that case, it's exactly the same as the precipitation reactions. It's just, remember, water and weak acids are our product. So HBr, strong acid, potassium hydroxide, strong base. So when we disassociate them, it makes H plus and Br minus, K plus and OH minus. We do the ion exchange here, so the positive from one and the negative from the other come together, and the positive from the other one and the negative from the other come together. And one of the things we need to remember, and this is true overall in these neutralization reactions, is that when we have H plus and OH minus coming together, that's going to form water, so 2 hydrogens and 1 oxygen. The other product is going to be potassium bromide. So this is a good example of what I was just talking about now. So now this really is just a soluble salt. I know it's soluble because it's attached to a group 1 metal here, potassium. And it's really not considered an acid or a base anymore. It's just a soluble salt. So you got to remember that sometimes you might have to apply the soluble salt rules. So I go ahead. So I was given my reactants. I draw my products. I make sure it's balanced. So in this case, it already is balanced, but I go ahead and make sure that it's balanced. And we talked about how do we do that in a previous section. And here comes the one tricky part inside of neutralization reactions, is where you disassociate the species to get to the complete Ionic equation. And so this is where it gets tricky, and you want to take a second and make sure that you get it right. So HBr is disassociated. It's a strong acid. Strong acids are disassociated 100%. So this is broken up into H plus and Br minus. KOH is a strong base, so it is disassociated into its ionic species, K plus, OH minus. KBr is a soluble salt, so it's not really an acid or a base anymore, but because it's attached to a group 1 metal, and that's the main rule that you want to remember, things attached to group 1 metals are always soluble. A soluble salt is disassociated, so that's still true in these acid-base reactions. So this gets broken up into its ionic species, K plus and Br minus, and then the last one, water, is really our product. And remember, we decided that we would not disassociate water, and we need to do that for something. Something needs to not dissociate, or we're not going to have a net Ionic equation. So water is our product. Water is not disassociated. So then to go from the complete Ionic equation to the net Ionic equation, I cancel species that are on both sides of the arrow. So here I have a Br minus and a Br minus, that goes. I have a K plus and a K plus, that goes. And what I'm left with is the net Ionic equation for the reaction of or the neutralization of a strong acid and a strong base, and that is H plus OH minus goes to make water. And that's really what we mean by neutralization. And a true neutralization, we are getting rid of the acid and the base, and we're just producing water. And the idea is, if you do a complete neutralization, you're going to end up with water at the end, or a pH of 7, which we'll talk about that later inside of this book. So water is considered the product, and this is something else to remember. For every net Ionic equation of a strong acid and a strong base, so if I identify that in the beginning, I expect this to be the net Ionic equation. So if you go through any time that you have a strong acid and a strong base, and I'm interacting them, and I say, what's the net Ionic equation? This should be the net Ionic equation I should get for any neutralization reaction between a strong acid and a strong base. And then lastly, so always a really common question to ask what the spectator ions are. Remember, those are the things that we canceled out from our complete Ionic equation to get to our net Ionic equation, and that in this case it was K plus and Br minus. So the next step is to start dealing with weak acids and weak bases. So the next step is to draw the net Ionic equation between a strong acid and a weak base. And remember, with weak bases, there's really two different types of them. There's the neutral ones that involve ammonia or some variation of that, and then there's the ionic weak bases, so things like F minus. And they look distinctly different, and so we're going to go ahead and do an example of both of them just to make sure that you understand what the differences are. So here I'm reacting HCl, a strong acid, with ammonia, which is our weak base. And I say, of course, draw the overall chemical equation, complete Ionic equation, and net Ionic equation. So here, this weak base, and with weak bases, remember we haven't talked about that. Really, these species, so like ammonia, do not disassociate in a reaction. So weak bases themselves do not disassociate during these kind of reactions, But that tends to be a little complicated. You'll see what I mean here in a little bit. But just remember, in reactions that involve ammonia or other amines, so amines like methylamine and things like that, the amine is not disassociated when we go through the reaction. So just remember that. So here, when I say find the products of the reaction, ammonia doesn't break apart. So we really don't have an ion for it. It doesn't break up into a positive or negative species. And so this is one of the places where it looks a little bit different than other acids and bases. Ammonia really just grabs onto a hydrogen, and that's it. So if I have H plus and NH3, what it's going to go to make is ammonium, and that's really the whole reaction. So see here, during this reaction, our product now, ammonium, is going to be a weak acid, and that's one of the other things that we expect. The chloride doesn't really do anything. It just comes along, and in reality, if we were to look at it, it's really just the counter ion for the ammonium. So Cl minus is the counter ion for ammonia. So when we do strong acid, strong base neutralizations with ammonia, you have to remember it looks a little bit different, and that the ammonia just grabs onto a hydrogen to form ammonium. So when you write the overall balanced equation, HCl breaks up to H plus and Cl minus. The ammonia grabs onto the hydrogen to become ammonium, and then we have just a chloride. So as always, we take a second and make sure that our reaction is balanced, and so in this case it is. And then the next step, we go to the complete Ionic equation. So we want to disassociate things. So as always, I take a second. This is the tricky part. Whether you disassociate something or not, that's a very crucial part of these type of questions. So HCl, a strong acid. Strong acids are disassociated. So we break it up into H plus and Cl minus. Ammonia, we do not dissociate. It's a weak base. Ammonium is a weak acid. So once again, it's vital to be able to look at something and say that's a weak acid or a weak base, because it affects whether or not we disassociate in these types of questions. Ammonium is a weak acid, so we do not disassociate it. So we actually consider ammonium to be the product of this reaction. And then Cl minus, it can't be disassociated more, so it just comes down for the ride. So ammonium is not dissociated. It's a weak acid, and overall we're going to find out that that's really the product of a reaction. So the next step is we cancel similar species on both sides of the arrow. So the only one that we have here is chlorine. We get rid of that, and then we get the net ionic equation, which is that ammonia grabs onto an H plus to become ammonium. And so once again, this is our real product for this reaction, and Cl minus was our spectator ion in this case. So just remember, with ammonia species, and like I said, there's a couple of variations of this called amines that really all they do is grab onto H plus, and so their reactions look a little tiny bit different. So you want to break that up when we say we're doing a reaction between a strong acid and a weak base. You want to really say, is it the weak base, ammonia-like, or is it one of those negatively charged weak bases, and treat them completely different. So here we're looking at the other example where our weak base is an ion, and it's still a weak base, but we want to go ahead and you're going to see it's treated a little bit differently. So we're doing the neutralization reaction of a strong acid and a weak base, and in this case we're using an ionic weak base. So our strong acid, HCl, and then our weak base, remember this is where the terminology gets a little weird. We're calling NaF, sodium fluoride, our weak base. But you've got to remember, sodium fluoride really isn't the weak base. It's really F minus is the weak base that's going on in here. So this is going to show up. It's just kind of an idea that you need to remember when we do the disassociations here, and we'll point it out when we get to that. And as always, we're drawing the overall balanced chemical equation, complete ionic equation, and the net ionic equation. So what was always the first step, you disassociate our reactants into their ionic species, and then you do the interaction between the different ions. So you take positive from one and negative from the other, and then the positive from one and the negative from the other and recombine them to make our products of this reaction. So in this case, when I recombine the ions to make our product, H plus and F minus makes HF, and then Na plus and Cl minus makes NaCl. And you're going to find NaCl is also part, you're going to see that a lot, but remember it's never going to be our product because it's a soluble salt. But NaCl is something that seems to pop up all the time inside of neutralization reactions. So I was given the reactants, I have found out what my products are. I take a second to make sure that everything is balanced. So here, just drawing it out, this is a balanced chemical equation. And then I want to go to the complete ionic equation. So once again, I want to take a second and make sure I correctly answer the question of, do I disassociate this or not? So HCl, strong acid, so it is disassociated. It's broken up into H plus and Cl minus. NaF, and so this is where I'm kind of hesitant to call NaF a weak base, because NaF is really considered a soluble salt. So it's a F minus is attached to Na plus. Remember, anything attached to a group 1 metal is soluble. So really NaF is a soluble salt, and it is, because of that, it is disassociated into Na plus and F minus. It's really F minus that is the weak base that's actually going to be part of the reaction. Na plus, we're going to find out, is a spectator ion. So it gets down into terminology, and when I'm doing these, I really don't like calling NaF the weak base, because people hear weak base and then they tend to think that they don't disassociate it, where no, I do disassociate this because the weak base is really F minus, and in reality Na was there just to make the salt, and we used a group 1 metal, so this would be soluble. So it disassociates and puts F minus into solution. So NaF, soluble salt, so we disassociate that into Na plus and F minus. Over here, HF, a weak acid, so it is not disassociated. And then here, NaCl, Na is a group 1 metal, and so because of this, it is disassociated into Na plus and Cl minus. So HF is really our product. So once again, one of our products is a weak acid, so that's very common. And as always, like I mentioned, NaF is disassociated because it's a soluble salt. Now it's really F minus that is the weak base that's going to be involved in this reaction. And we will see that when we get to the net ionic equation. So the next step, I disassociate species on both sides of the arrow. So here I have a Cl minus that goes, Na plus that goes. And what I'm left with in my net ionic equation is that H plus and F minus react to become HF. So here, this is our weak base. Our weak base is reacting with H plus, and that is making our product, which is a weak acid. So this is our weak base. Once again, our spectator ions were Na plus and Cl minus. So here, the next one is taking a weak acid and a strong base and doing a neutralization. So our weak acid in this case is HF, where we're reacting it with a strong base, NaOH, and we're going to draw the overall neutralization reaction, or what's going on in the reaction between the two. First step, I break my reactants up into their ionic species. So HF is broken up into H plus and F minus. NaOH is broken up into Na plus and OH minus. I then recombine the ions. And here I remember that when I take H plus and OH minus and I combine them, what I end up making is water. So that's going to be one of my products. And Na plus and F minus come together to make a soluble salt NaF. So The reactants were given, the products I've found out or determined. I go ahead and draw the overall balanced equation. So here our reaction is balanced, and I want to disassociate the species. So once again, I take a second. This is where it gets a little tricky. HF is a weak acid. So weak acids are not disassociated, so it's not broken up. NaOH is a strong base. Strong bases are disassociated, so we go ahead and break that up into its ionic species, Na plus and OH minus. NaF is a soluble salt. So remember, we were just talking about that. It's not really truly weak base. It is a soluble salt, so that's broken up into its ionic species, Na plus and F minus. And then water, we have decided that we do not disassociate water, so that remains. So remember, HF is weak acid, so we do not disassociate that, and NaF is disassociated because we consider that a soluble salt. So I go through, cancel species that are on both sides of the arrow. The only one in this case is just Na plus, so we get rid of that to get to our net ionic equation, and that is HF is reacted with hydroxide here, OH minus, to make water as our product, and then F minus. And really, Na plus is the only spectator ion. So that is the kind of the basic combinations of strong and weak acids and bases and the different types of dissociations that can come together. These can be a little bit more complex. You got to remember, some acids and some bases may have, some acids may have more than one H plus, some bases may have more than one OH minus, which will, kind of complicate things a little bit, and it just means that you have to balance things. The last thing I want to talk about is gas-forming reactions. And this is a common idea when you're doing neutralizations, is sometimes you will see that a gas is formed. So when you mix two things together, you mix your acid and base, you'll see little bubbles forming. And a question will ask, what's the bounce reaction of what's going on with that? And so I want to show you a little trick that if you don't know this trick, it can be a little complicated trying to draw the products and bouncing them. So when you see a gas form, typically what is happening is that you are forming carbonic acid, H2CO3. When you form carbonic acid, it is unstable and it almost immediately falls apart into CO2 gas and water, and it's this carbon dioxide gas that you're actually seeing as the bubbles. So what we're going to use is this reaction that carbonic acids, H2CO3, is really the equivalent to CO2 and H2O. So we're going to use this idea here in just a second when we draw out our balanced reaction. So I take HCl, I add it to sodium bicarbonate, Na2CO3, and I write the balanced reaction. So I'm not going to go through every step, but when I do the combinations of ions, I make carbonic acid, H2CO3, and NaCl. I go through and balance it, and it looks like this. But remember, we don't want the carbonic acid. We want to show the reaction that involves forming the CO2. So what I do, and this is the trick, is I go ahead and bounce the overall reaction, and then I understand that H2CO3 is equal to this. So I bounce it first, and then I substitute the H2CO3 with the CO2 and the H2O. So I get rid of this, I substitute it, and then this is really the reaction that's occurring when I'm interacting my acid with sodium bicarbonate. So it's a lot easier to do that. If you add this CO2 and H2O and then try to balance it, it can be a little tricky. So I just go ahead and balance it and then do this substitution to get to the product.